Good morning. Welcome to Krishna's classroom. We had been continuing the narrative on LP spaces, consolidating all the results that we have proved in detail. Now, the first part of which dealt with the construction of the linear space LP. Now, you know that it involved a lot of intricate steps to arrive at the normed linear space. And LP X or LP mu is in fact, this is what you have. You have X and mu, as we have defined earlier. And then we have the space LP mu and with its norm defined by norm of F one by P less than infinity. In fact, this is the one, whereas norm F defined as essential supremum of mod fx for x belonging to x. Now, then we proved that both LP and of course this naturally induces a metric which you call dP, so we are looking at LP mu as a normed linear space. Is a normed linear space, and hence metric space. Therefore, you see LP mu has a topology of it. Now you know that any metric space, it's a metric space. Any metric space has a unique completion. Completion. And what do we mean by the completion? In the sense that all Cauchy sequences that is convergible has a limit in the space. This is a very general result. And this completion is unique in the sense that two such completions are always isomorphic to one another, indistinguishable. Indistinguishable non-distinguishable structurally. Consequently, LP mu as a completion. Has a unique completion. Okay. Now, what do we mean by completion? It simply says that this space can be embedded in a larger space. Okay. This can be embedded in a larger space. And the larger space is complete. So I'll put it this way. If YD is a metric space, and D equal to D tilde D equal to D tilde on. Okay, that is every Cauchy sequence by 3. Now, the situation can be understood easily. Look at the set of rational numbers with the usual metric. For example, You take Q with the usual metric is not complete. That is, there exists Cauchy sequences in Q which do not converge to an element in Q itself. Okay. For example, you consider the expansion for E. So E is Q. But you look at this sequence. K factorial is a Cauchy sequence. And converges to and does not converge. It's a Cauchy sequence which that does not converge it. In fact, it converges to E. E is not a rational number. Okay. So, in fact, it converges to E, where E is not a rational number. To the exponential number E, which does not belong to E is a real number. In fact, one can prove that R turns out to be the completion of Q. Okay. And is complete. Whereas Q is not complete, but R is complete, which in turn tells that every approximated as closely as we require or we shall say that Q closure is equal to this is closure. to closure is equal to. Naturally, so LP mu completion. But what is it? If LP mu itself is complete, then itself is the completion of So naturally, the question that we want to first ask is, so what we prove at this stage is that LP mu is 8. That's a great result. Answer is that means the theorem Cauchy LP then as sentence 2. So this is the completion theorem. Okay. Now one can recall the proof of this, but I don't want to do it. But that is already done in detail. Okay. What one does is you extract a subsequence from it, okay, which you can show that pointwise converges almost everywhere, and the limiting function you designate by f, and then one can show that the original sequence Fn converges to that f in the LP norm. That is the strategy of the proof. So I don't want to do this. So what are the other consequences? We have the following theorem. So two results that are useful. If 1 less than or equal to p less than or equal to infinity, and Fn is a Cauchy sequence in the limit f then Fn has a subsequence Fnk which converges pointwise almost everywhere where that is except belonging to a set of efficiency. This is a useful result because our convergence is in the LP norm. So you are asking, does this mean that the sequence Fn converges pointwise to F? The answer in general is no. One can construct examples for this. But what one can assert is that there is a subsequence which I have designated by Fnk k running from 1 to infinity of the given sequence Fn, which converges pointwise almost everywhere to Fx. That means, except possibly on a set of measures 0, everywhere else Fnkx converges to Fx pointwise. Okay, so that's the result that you have. Again, we have proved this result, or in fact, the proof is embedded in the proof of the completion theorem. Now further, so next theorem is, this theorem turns out to be a useful tool, because what we are saying is that we can approximate it f by simple functions satisfying certain conditions. Okay, so let complex valued measurable simple functions of with one more attribute, that the measure of as a simple function, we use the notation S. Not equal to 0 is finite, such that the set on which the function is not equal to 0 has finite. Now this is valid only for one lesser or equal to p less than infinity, and not when p equal to infinity. It's a beautiful result, very handy result. Look at the nature of the function. The function is a complex value, measurable, simple function on x, which means the function s takes only finitely many values. And for each value, y, a complex number, S inverse of set on which it Sx equal to y is measurable. Is measurable and measure of the set on which is finite. That means it takes only finitely many values. So you are taking the union of these sets, these measurable sets, and the length of such measurable sets is finite. That's the assumption. That therefore clearly you see that integral of finite. Therefore S belongs to LP. So that is satisfied. Okay. So S such functions or the S is contained in what we assert is that S closure. That means any element in LP mu can be approximated by as closely as you want by a complex valued simple measurable function with this particular property. Okay. Right? With this particular. Right? So, or by an element in S. This is what we have proved earlier. It's a beautiful result and very handy one, because instead of working on F, quite often we can work on such simple functions and then apply the limiting process to get the result. Okay. So these are the advantages that you have while working on a dense subspace. On the dense subspace, to prove the certain properties and so on, it may be much easier because the structure of smoothness, structure of say this kind of structure or any such thing will be much simpler than the structure that is available in the closure of it. Or in short, what you are saying is that S closure is equal to LP. So you can approximate any function here by a function in S. Okay, and one can easily run an approximation. Okay, so this in turn tells you that if F belongs to LP mu, that converges F converges to F and this is the property that can compute the integral of F as closely as you want by functions in the sequence, the integrals of the functions in the sequence. image is equal to 0, or integral you can approximate it by integrals of the function, or in fact it is the approximation of this. Therefore, you can compute it as closely as you want using these essence. Essence are easier to handle. Okay, you know that takes only finitely many values and it's measurable, complex value, etc. Therefore, it is very easy to this integral. So that's about that. Now we go one step further. So far we have not put any restriction on x other than that there is a sigma algebra and a measure on that. So it's a measure space. This is the restriction that we have. Now we are going to impose a topology on this. Okay. So far we have not assumed any topology on assumed any topological structure on X. Now you see, so the theory is quite general that way. Okay, whether there is a topology on X or topology it is not there on X, then still it works. Now let us see what more we can say if there is a topology on X. Now I'll tell you the reason, because if X does not have a topology, then you cannot talk about continuous functions. Okay, because you are talking about functions f from X to C. Now you take an open subset of that and pull it back. There is no structure to decide whether that pullback is a open set or not. Okay. Therefore, if you have a topology also on X, then one can talk about continuous functions. Now, this is the greatest advantage. And you know that the continuous class of continuous functions on usual sets where there is a topology, where it is sensible, is a huge class of functions with several advantages that we have for computation. Okay, and this structure enriches the entire environment. Okay, and what we are going to do is to see what it comes out of. Therefore, let us choose such a set. So we take X to be locally compact Hausdorff space. That is something which requires a topology. So on X you have a topology, and with respect to that topology, it is locally compact. That means every point in X has a neighborhood whose closure is compact. Okay. Secondly, it is a Hausdorff space. That is the nice separation properties hold. I mean you have nice separation between two elements of X. Okay. So if you take two elements of X, you can separate them with open sets. Okay. So this is what you mean. It's a Hausdorff space. So these properties are assumed. So it is not merely it's a topological space, but there is an induced structure assumed. Now you see what kind of advantages do we have with the presence of such a thing. Now let us give an example. An example for this is, of course, X equal to Rn with the usual metric is a locally compact Hausdorff space. That's an example. Now we shall put our notation here. Let CCX is an example. CCX we take as F complex value measurable or naturally continuous on X with compact set. That means we are taking all continuous functions, complex valued continuous functions on X that continuous because you have the topology now assumed on X and with compact set. That is you take the set of all X take the closure of this. This is compact. It's compact. Okay, so this is the closure of this. I put this bar. This bar is to go with set, not underlying this compact circuit. Okay, this compact. Now that's the definition of it. Okay. So M is the sigma algebra on X induced by lambda. Okay, lambda a linear function on CCX. So you know that CCX is a linear space, and we can talk about linear functions on that. And this, once you have a linear function in the Rees representation theorem, you have proved that theorem asserts that there exists such a sigma algebra, and be the induced measure. So we take, what you do is take a linear functional on CCX, okay, and then by Rees representation theorem, it induces a sigma algebra on X as well as a measure on mu, and they are all connected in the following way: lambda f is equal to integral over x ft. This is the linear function. Now, for example, we come back to Rn or Rk. So here I end. Example, RK with Lebesgue measurable sets of Lebesgue measurable sets and mu is the Lebesgue. Let's say example. Now what one can prove is the following. So we put the density there. Less than infinity, CCX is LP beta. This is a nice result which says that through continuous functions with compact support, you can approximate any element of LP in the LP norm. Okay. That means see, this has lot of attributes, that it is not only a continuous function, it has only compact support, such that is less than. That means f can be approximated as closely as you want by a function in CCX. That's a beautiful result. Because now you have used the structure of that is available on X also. That is the topological structure that we have made use of. And that becomes very handy while working on such functions. Now, what happens for the case p equal to infinity? This is something which merits special consideration. For p equal to infinity, norm of f x, and this is like that. In an infinity. Define C naught x p equal to F with the property that for every epsilon positive, there exists a compact set which depends on F and epsilon. Or I'll give an example, it will be clear. So for instance, you take x equal to r with the usual no. Okay. Now you see that if you take fx equal to one upon, suppose you take this function. This function has the property that it dies down at both plus infinity and minus infinity. Yes. What is the value of this function at x equal to 0? X equal to 0. See that the function takes the value 1. And then it dies down at infinity. Both plus infinity and minus infinity. Symmetric about the y-axis, and this is what fx is. Now we just apply this criteria. So this function, now f belongs to, but f is not, does not belong to CC. It has no compact support. Okay. Its support is the whole R. Okay, it is not compact. Therefore, this is the example of a function which is in C0 R, but f belongs to CCR. Now, you look at this function. Okay. Now we have CC is properly contained in C0 R, and that is again properly contained in, for instance, see identically equal to 1, then f belongs to, but f does not belong to C0 Now another example is fx equal to plus 1 f belongs to C not R, but f does not belong to, I'll put G here, G does not belong to CC, but you can actually show that every function in CCR is also in C naught R, is also in L infinity. So this relationship is following. It's not true. That is valid. I give example. Okay. Functions in C naught infinity are set to now this is just a terminology, because in a general X you may not have a notion of infinity. Okay, right? For instance, you take X to be equal to, say, the interval or the interval minus 1 to plus 1. Okay. Compact interval minus 1 to plus 1, then all functions its compact support are also C naught. Sorry, you have is this is suppose you take what? Now this is not compact, but its closure is compact. Okay. Therefore, you see that this particular property is valid there, and C naught X functions do have tend to 0 as X tends to minus 1 or plus 1. This is the property that okay. So there is no infinity there, but this property is valid. Okay. So here there is no infinity that you are talking about, but this is that's why I said it is a terminology that is borrowed from the situation when X is equal to R or X equal to RK, right? So just keep that in mind. Now the theorem that we have proved is the following. So the theorem that we have proved is following. Then we prove that closure, this is the L infinity closure, is equal to Okay, this that is the theorem that we have. So we have, in fact, we can prove that C naught x, this is the result that, okay. So C naught x is right, and is the completion of therefore, if you take C naught x, its closure is CCX, and which is not equal to L infinity. Okay. So the previous result is valid for P1 less than or equal to P less than infinity, and not when E equal to infinity. I think these are the results that we have proved. All these are very useful results in analysis. Okay, thank you very much. We conclude the chapter on LP spaces here, and the last two lectures, namely the lecture 78 and 79, sum up the content of the abstract integration theory, and which is probably, I would suggest that people read these two first and then go to the details, so that the LP spaces can be very clearly understood. Thank you very much. Come up with another topic later.